Hi, all. This is Vasu Sham, and we're theoretically podcasting. Today, I'm joined by Rifath Khan and Goncalo Regado, and we're going to talk about Cauchy slice holography, which has been the focus of these gentlemen's research during their PhDs here at the Department of Applied Mathematics and Theoretical Physics in Cambridge. So, could you describe briefly how it is you entered into this project? I guess we could start with Rifat, and you guys can take turns.
So we started this project during our first year of PhD,
Okay.
and so like Aaron came, dude, you
There's a good story here. This is what I'm gathering.
Yes.
Okay, so
in our first year of PhD,
yeah,
that was Aaron.
yes, Aaron Wall. So just
Aaron
to be
Wall,
clear,
yeah, our
you're
PhD
working,
supervisor.
yeah.
We started our PhD together at the same time.
and the paper we're going to discuss today was written by the three of you.
Yeah.
Yeah.
Good. Okay.
So
It was like first day we got to the department. Aaron invited us for lunch. He said he wanted to share an idea. It was like
Okay.
this, I remember.
Okay.
And
He
we
had
went
some-
to Churchill.
yeah, he had some idea about tensor networks being beyond toy models,
Hmm.
something like that. And then tensor networks, you can think of it as field theory partition function. And he wanted the field theory to now be living on Cauchy slices.
Okay.
As
Yes, he
opposed
wanted,
to
to do the cosmology.
Right.
He wanted the holographic description of cosmology.
That was the ultimate goal, is to
Yeah.
really get to
Yes.
cosmology. And somewhere along the way, you realized that you needed to have the dual holographic theory end up on the Cauchy slices,
Mhm.
essentially,
Yes.
right? So that's kind of the picture that we're driving to. But what's amusing about it, I mean, there are many things that are interesting about it. But one of the things is that this formalism, at least from the bulk perspective, ties in with like some very old stories about quantum gravity. And in fact, like the oldest story about what we call canonical quantum gravity, which is that of Wheeler-DeWitt from the 60s, where they identified that you have physical wave functions in the theory of quantum gravity that are subject to a constraint equation, and that this constraint equation is also the Hamiltonian of the theory. So Arnold, Dieser, and Misner had already done this analysis for the classical theory, right? They worked out what the Hamiltonian of general relativity should be, and they showed that quite generically, right, as in without any assumptions about the asymptotic boundary and what it should be, or that there are any asymptotics, they showed that the total constraint or the total Hamiltonian of general relativity is just a constraint. It's a sum of the diffeomorphism and Hamiltonian constraints.
And with the boundary term.
Right. So for now, we're just saying that there are no boundaries, like in this case.
Okay.
And then it was Wheeler-DeWitt that tried to ask the question of how to quantize this system, right? Given by the phase space of the Arnold-Dieser-Misner Hamiltonian, its conjugate variables, which are a metric adapted onto Cauchy slices, and its conjugate momentum, which is related to the extrinsic curvature of this surface embedded into space-time. And that's all very nice. And we had later, or I'm not even sure about the history here, the chronology, but there was perhaps in parallel these ideas about the so-called gauge gravity duality, which just came from thinking about how black holes have an entropy that scales with the area of their event horizon as opposed to their volume. And that just gives this intuition that there should be some localization of degrees of freedom onto the boundary of some given region when quantum gravity matters. And this led to a proposal which in some sense is conservative to say that, well, actually, these are the degrees of freedom of the quantum gravity theory, right? That it isn't just some illusion. The illusion is explained by positing local physics on essentially the analog of the event horizon in just more general setting. And later there was what some would call a third string revolution with the discovery of ADS-CFT, which was like a concrete example of this. And there's been a lot of development in that direction. And the Wheeler-DeWitt equation was there in the annals of history and kind of left there, right? Some people in loop quantum gravity tried very hard to solve it. They had partial success, but there was no understanding like there was in this picture of the gauge gravity duality, that even on some special spaces with negative cosmological constant, what it means to do quantum gravity there. And now what you guys have done with Aaron is come full circle, well, which I thought was worth mentioning, that now you have a way of actually taking this old intuition and realizing it in a context that's consistent with this other old intuition about quantum gravity, which had to do with, you know, thinking about black holes, understanding the localization of degrees of freedom to one lower dimension, and so on. So you did mention, though, that the initial motivation came from tensor networks and holographic cosmology. So why was it clear? I mean, was it clear to you why it had to go in this direction at the time, or maybe even now?
For me, initially, I didn't care about tensor networks. I really thought it was just a toy model. But the fact that you can write down solutions to the Wheeler-DeWitt equation, that sort of fascinated me. And so the Wheeler-DeWitt equation, it's a hard equation to solve.
Right.
But if you can find some way to solve it, like for example, you can take start with the CFT partition function and then deform it in a particular way such that it gives you a solution to the Wheeler-DeWitt equation.
Right.
And also just from the mathematical form of what a Wheeler-DeWitt state is and a field theory partition function is, they're of the same mathematical form. And so it's in the beginning days of the project, it was like, so maybe we can interpret a Wheeler-DeWitt state as a field theory partition function. What's stopping us? Nothing. So that was one of the motivations.
And there was some connection with recent literature, part of which you were involved in as well.
Right.
In which people were trying to understand the boundary field theory partition function in the context of ADS-CFT, also as a Wheeler-DeWitt state, but in a radial slicing.
Yes.
Of cylinders.
It was sort of a sideways equation.
So that also gave a strong hint that this might be possible.
Right. So the novelty, I should say, okay, this was built on in stages, if you wanted to think about it chronologically. Yes. That there was an understanding very long ago of what should become of what we think of as the bulk constraint equations when we have asymptotically ADS boundary conditions, and that it should be the asymptotic symmetry of the theory manifests itself as purely the boundary contributions to the constraint equations, and what's left of the constraint equation should just tell you that there is conformal invariance on this boundary. And indeed, every CFT respects those invariances. The special ones that feature in the most detailed examples of ADS-CFT have a little bit more than just that symmetry, and the supergravity theory is that they're dual to also mirror that structure. So in many ways, that part of the story was pretty well understood. What was not understood is what happens when you actually bring this boundary into the bulk, so to speak, that when it encloses a finite space-time volume, then you don't have the same arguments that tell you that the constraint should somehow simplify. I mean, you just have to deal with the fact that when you drew this boundary, it has to solve the constraint equations, which means that it's subject to dynamics, and it is whatever it is. You need to understand what happens. And that's when you realize that there's this sort of sideways Wheeler-DeWitt equation that it needs to satisfy, at least in the semi-classical limit. And what you guys managed to do was take this picture and sort of bring it, instead of being like a cutoff surface that goes along time-like direction, to a constant time slice as in a Cauchy surface, which is itself space-like and has a time-like normal.
Yeah, the goal was to quantize gravity the way you quantize any other theory.
Right. So
foliate in time slices, and you try to write states.
Exactly. So this is like, in other words, going back to the original mission of Wheeler and DeWitt in taking the Arnowitz-Dieser-Misner formalism, their phase space, and just quantizing it in a canonical way. And we'll get to why you might have done better than them, which is an important distinction to make. So before that, there's a very useful, well, how should I put it, infographic in your recent paper which I'll just pull up. Great. So basically, what we should do here is just run down this table. So the rightmost corner is what happens in field theory, and the leftmost corner is what happens in mechanics, but well, it could equally well happen in quantum field theory. And the middle is the thermodynamics. And all of these are somehow relevant to how we've been thinking about gravity in recent years, right? If we consider the past few decades to be the recent years. So as I was mentioning, in quantum field theory, you have a partition function that is a functional of sources, right? And sources have a canonical conjugacy to operators because we generate or we compute expectation values of operators and their correlation functions by differentiating the partition function with respect to the source. So it would make sense if I had something that looked like JO to kind of consider them to be conjugate to each other. In much the same way as how we have a conjugacy between positions and momenta in mechanics, and how we have a state which is a function of half of these, that is just the positions or just momenta, and the other object and its correlation functions are computed by taking derivatives of this with respect to the other.
Yeah.
Right. So this is, again, this was probably what you meant when you said that these two things have a similar feel to them. And there is indeed an analogy in thermodynamics. And I think that this was maybe historically the first place where people actually talked about things like phase spaces, and it was a sort of export into mechanics even, if I'm getting this right. So there was these notions like volume and pressure that are extensive and intensive in thermodynamics, and that there's conjugacy encoded in the relation between the free changes in free energy and the changes of these quantities. And in statistical mechanics, you just have a partition function like you do in quantum field theory. So it's there. It's just literally the same thing. But now what we're going to do is proceed to look at how these conjugacies actually manifest in the dictionary, in the sort of gauge gravity duality, right? And so there it becomes just a matter of understanding how to take one object and have it be the solution to the equation that the other object satisfies. And is that fair to say that this is kind of the goal of your paper? So I should mention that this is the paper that we've been referring to, which came out in September of this year. At least the most recent version. The most recent version. So if we go stepwise, again, in the chronology, this was the picture that came first, which has been discussed on this podcast a couple of times before. And so we can
also worked on these things, right?
Yeah. And that was also the reason why these things have been discussed on the podcast before. But the basic idea being that the ADS-CFT picture that would take place as a correspondence between what's happening inside the tin can and happening on its surface, which is the asymptotic boundary, is deformed in a technical sense when you bring this boundary inwards, right? And the deformation is a so-called T-squared deformation, which is an irrelevant operator deformation of the CFT living here. And indeed, the equation that tells you how to move in this direction is related to the constraint equation. So starting from there, perhaps it would be good sort of jumping off point for explaining how to get to the Cauchy slices. If you may.
Sure.
Yeah.
So to get to the Cauchy slices, we need to take the suggestion of that table seriously. So before, in that table, there was this analogy between mechanics and field theories. And if you want to do quantum mechanics of gravity, then we're going to write wave functions on configuration space, where the variables in configuration space are just the metric on a slice. So imagine a slice, which I'm going to call sigma, which has a metric G. And the idea is to notice that there's a very close resemblance between this and the partition function that lives on the same slice sigma. But now the source That was this was a generic term for a source. One of the sources that you always have in a field theory, in a local field theory, would be a metric, background metric.
Right.
So you just imagine this lives on sigma, and formally speaking, they have the same,
Right.
they're the same type of functions.
But I mean, one, again, conceptual difference that we should make clear here is that unlike what we normally think of when we say gauge gravity duality, it's not a description of, or it's not a correspondence between a partition function that we normally think of as living on the boundary,
right,
and something happening in the bulk, but really that you have this partition function living on a Cauchy slice.
Exactly.
So okay,
let's say if we wanted to quantize gravity, what would we have to do? The gravity has the diffeomorphism invariance.
Right.
And that is at the quantum level encoded by two equations. First one is called the Hamiltonian constraint. Where this x here is just a point on the slice sigma. So this quantum gravity state will live on some abstract slice, call it sigma. Don't necessarily think of it as a Cauchy slice necessarily for now.
Right.
It eventually will get that interpretation, but for now it's just a three-dimensional spatial slice. We want to write a state that is a superposition of metrics on that slice, and we want to study then what dynamics emerges from this. And one of the equations it has satisfies the Hamiltonian constraint, which in a sense encodes invariance under time diffeomorphisms of this slice.
Right. Sort of normal deformations of the slice.
And the other one is the so-called momentum constraint, which encodes invariance under changes of coordinates on the slice.
Mm-hmm.
So you have freedom to choose any coordinates you wanted here to parameterize your slice, and if you change those coordinates, your state should be invariant under that. So this is what this equation tells you. So in particular, this equation is simple to solve. It just tells you that whatever state you write down has to be written down of functions that are invariant under these transformations. So this equation has been known how to solve forever. Problem is solving this equation. Let me write the form of the Hamiltonian constraint first. So classically, I'll write down what the Hamiltonian looks like. So this is just what we would usually write down as a Hamiltonian on the slice. There's a kinetic energy term and the potential energy term.
Right.
So this is literally kinetic energy density plus potential energy density. And this pi b is just a rewriting of the extrinsic curvature. It goes like the extrinsic curvature minus its trace. So that's why I'm saying this is a kinetic energy term, because it goes like derivative of the metric with respect to time squared. So this is classically what the equation looks like. And then usually when you quantize in the canonical framework, what you do is write down the conjugate variable to your metric in terms of functional derivatives in a metric representation. So this, you'd equate it to this. And then you plug it in here. And you have a functional differential equation at every point on the slice. And you have to solve
second order.
Second order, yes.
Right.
And there's some ordering ambiguity with these derivatives, and you can pick some ordering and proceed with that. So the question is how, once you do this, how to solve the equation. And that question has been there for many decades.
Indeed.
And if you solve this equation, you'll get, what will you get out of it? What it means to solve this equation means to write down a superposition of metrics that satisfies this constraint. And once you do that, that's a quantum gravity state that would tell, from which you could extract information about dynamics and other things that happen in your quantum gravity system. And whenever I write, in general, the kind of variables you could have on this slice sigma are, you have the metric, as I pointed out, but you could have other matter fields as well. These stand for matter. So in general, your state will be a superposition of metric and matter field variables. And this will encode correlations between these two. And if you have matter, there'll be some extra terms in the Hamiltonian constraint corresponding to matter. So the question is how to solve this thing. If you want to write stuff as well, you can let me know.
Okay.
And what we did in our paper was, in a sense, find the vast class of solutions.
Indeed.
We have plenty of arguments between ourselves whether these are all the solutions or not. The most conservative answer is a vast class of solutions.
Sure.
And what do these solutions look like? So we will see that up to now we were just doing canonical quantization. We're not talking about holography at all. But people, since the discovery of holography, they believe that holography is a property of gravity, a holographic encoding of degrees of freedom. And we'll see that holography will, in a sense, emerge from just trying to do this canonical quantization. There will be like a merging of the two ideas.
Okay, so we're sticking with gravity.
Sticking with just gravity, so just a variable g. And it turns out that the class of solutions we found looks something like this. Yeah. So I'm going to write in terms of a field theory partition function, because it will be obvious in a second why I'm writing it like this. It will be obvious now, actually. The thing is, we start with a CFT partition function living on sigma. So I'm going to put sigma here just to remind the audience that everything lives on sigma. So we have a CFT partition function that lives on this same sigma where the eventual state will live. And that has a source that's a metric. Corresponding operator to that is the stress tensor. And we're going to modify this CFT partition function by an operator. And I'm going to write this in a particular way.
At this point, it's also worth noting that this field theory partition functions, they are automatically spatial diffeomorphism invariant.
Right. And that just has to do with the covariant conservation of the stress tensor of these theories, right?
And so they automatically satisfy the diffeomorphism constraints,
which
is equivalent to what you said.
And that is a very important point to underline, because in all the discussion about these deformations, like TT bar and its higher dimensional cousins and so forth, the assumption is that if you put all these on flat space, you're maintaining certainly the translation ward identity, which will then become the covariant conservation of the stress tensor on an arbitrary background. So yeah, that's good. The harder one is, I guess, what you're getting to is to solve the related.
And there's one more thing that I have to point out. It's not just the Hamiltonian constraint we have to solve, but let's for now try to do that.
Okay.
So I'm going to write a modifying operator that I'm going to explain what it means now. So this is an operator, which means it's something that includes derivatives with respect to the metric and so on. So it's a differential operator with respect to the sources. And it is parameterized by a parameter lambda, which means, and this parameter lambda is a parameter along the flow. So we start with, if you think of this in theory space, we start with this CFT, that is the thing on the right-hand side, and we deform along a particular curve in theory space, and that curve is parameterized by lambda. And we're going to flow until a particular point mu. So here is lambda equals 0. Here is lambda equals mu. Flow parameterized by lambda. And at every point of the flow, you have to update what the deformation operator is. And then you flow in that direction, then you update again, which is why you have this path order exponential.
Right. So basically, you're positing that there's a differential equation, an ODE, that looks like the derivative with respect to lambda of this object
Yeah,
equals this operator acting on this object.
exactly. So there's, in a sense, there's exactly like a Kalan-Zimanzik equation,
Right.
which encodes an RG flow. The partition function that we have at value lambda is equal. I'm not going to write the signs now. To this, the derivative with respect to the flow parameter lambda is equal to this operator, differential operator O of lambda acting on this same partition function. So one important aspect of this equation is that notice that because we started with the CFT, there were no scales in this theory.
Right.
And now we introduced a lambda that is a parameter along the flow, and this lambda is dimensionful. But it is at the moment the only dimensionful parameter. So let's say we flowed up to here, and this is the theory at this point is defined like this. And now we ask, okay, I can compute some correlation functions here, and then I ask, what do they look like in the infrared? And because the partition function was built exactly by solving this equation, that guarantees that the RG flow will exactly be in the opposite direction,
Exactly, yeah.
all the way up to the CFT you started with. So we can have the interpretation that the IR limit is this CFT.
Right, and then this flow basically is taking you in an irrelevant direction.
Yeah. So when we think about deforming the theory from the CFT, it is via an irrelevant operator, which is this O of lambda. Once we have deformed it all the way to the point that we want, we have a field theory defined there. That's the field theory. And then if you want to ask questions like what is the large distance limit of correlation functions, then you'll essentially fall backwards to this. So you'll recover the CFT correlation functions.
Also,
yeah,
in general, like you just put a random deformation of the CFT. It would not necessarily be an RG flow, but we're going to choose something, a special thing, which would satisfy another equation where the action of this O on this whole partition function is equivalent to the action of the while generator on this partition function. So what the while generator effectively does is it does a while rescaling to the field theory partition function. And since that is also achieved by hitting this operator O, you effectively get this change in lambda to be just a while rescaling. And so changing lambda is just an RG flow in that sense.
So this exactly what Rifath was saying, this operator here encodes exactly while rescaling of this partition function. And okay, so we have this partition function defined up to here, and then there's one more thing because there's one more space to fill in, and that's just some counter terms. Maybe I should write it as we write in our paper. Yeah, just some factor. This is just some universal functional of G. So it doesn't change the theory per se, just relabel some canonical variables. But really the meat of the story is here in this deformation. And so in our paper, we show how this prescription, starting from any CFT, will give a solution to the Hamiltonian constraint. So this Z living on sigma as a function of G satisfies the Hamiltonian constraint at every point on the slice sigma.
Right.
Now, there was another thing I said, we have to not only just satisfy Hamiltonian constraint, there's an extra thing. Okay. And this is very related to the fact that this operator is made to satisfy this. And because you might ask, what is this operator? I mean, I'm just telling you that there exists such an operator. Can you construct it? And in our paper, we construct it. And it turns out that the key to construct it is to notice that in quantum gravity, not only did we have the constraints operators h of x and dA of x that have to annihilate the state, there's also a constraint algebra. And the constraint algebra has obviously all the possible commutators you can take, a crucial one being this one. If you take commutator of Hamiltonian constraint with itself at nearby points, it goes like there's a local interaction term. It's not zero. It doesn't
Right, but it's proportional to the diffeomorphism.
It's proportional to the diffeomorphism constraint.
And indeed,
so this
when
is
you
crucial.
satisfy the constraints, it'll vanish. So indeed, it closes.
It closes on the
But
constraints.
it closes on like in this very specific manner, and that is what's constraining about this algebra.
Yeah,
Constraining in a different sense of the word. And that was well, half of my PhD was spent trying to make sense of this fact.
So,
but no, for sure, it's important to.
So we have to also, in a sense, under this deformation, there's a picture that we can draw here. We start with this CFT that is flowed by this deformation parameterized by mu to the Z sigma of G that I called earlier, the deformed field theory. Now this CFT satisfied the Weil constraint.
Right.
Where this W of X is just the Weil scaling operator,
right,
including the anomaly potentially.
Which is basically the word identity for Weil transformations, potentially anomalous.
Yeah.
It's the anomalous word identity corresponding to Weil transformations of the CFT.
Exactly. And a property of the Weil rescaling operator is that it commutes to itself. This is like a Westominowit constraint.
Yes.
Consistency condition or whatever it's called. You have something in your papers about
this. Well, I mean, the only point I made in my papers was that this will always be true in any given RG flow. You can always do this. You can take a CFT, deform it by some operator. You can use the dimensions of the coupling of that operator to create a scale factor for your CFT. And so you can always write the Kalan-Szymanczyk equation as coming from doing a Weil rescaling of the CFT, right? And then what happens is that the response of the CFT under that rescaling, right, even away from the fixed point, is some extension of this anomalous word identity, and the extension is typically given by beta functions.
Okay.
So beta functions times the operators. And what people do in the so-called local renormalization group approach, or the local renormalization group literature, which is also a product of Cambridge, by the way, because Hugh Osborne and Ian, mostly Osborne and Shore were like at the heart of it. They figured it out. And what they did was they said, well, you have these constraints on beta functions and anomalies coming from the fact that Weil transformations have to commute. So their prescription was you start by expanding this into the Weil rescaling generator acting on Z QFT equals anomaly plus beta functions times the operator expectation values plus all this other stuff. Plug it into this. Right? So you just write everything consistent with power counting in this equation, the top equation, and then you just go through and compute this commutator, and you'll find that demanding the closure of this commutator will require all sorts of constraints that the beta functions as a function of sources, the anomaly, etc., have to satisfy. Some obvious ones are that, well, box R in 2 dimensions doesn't contribute to the anomaly. In 4 dimensions doesn't contribute to the anomaly. And also in 2 dimensions, you can show that you can use this procedure to prove a strong version of the A theorem, or the C theorem in 2D, which is that you can show that the beta functions satisfy a gradient flow, and then the object that you're flowing with respect to is the C function. At the fixed points, it becomes constant. So these were very impressive results. I mean, I thought that they were very interesting. And clearly, you want to understand how to play this game with some holographic field theory, holographic CFT, and discover the constraint equations, bulk constraint equations, as a result of doing this.
Yeah.
That was the goal. But now this equation is actually not constraining enough by itself. It needs the information in the bulk GR constraints. So there's something beyond just the regular rules of quantum field theory extrapolated to the case of some holographic CFT, which is still a regular quantum field theory, that needs to be satisfied. So this is actually a sort of bottleneck that like holographic field theories need to pass through.
Yeah.
Right. And so that was kind of the point of my the papers I wrote about this.
And in our paper, that intuition helps us a lot in the following sense. So along this flow, you can imagine that the constraint you need to satisfy also, in a sense, flows to some different constraint, which is the Hamiltonian constraint.
Yeah.
And the algebra of constraints that you were satisfying originally also flows to a different algebra. Now with the updated Weil rescaling operator, in a sense, which obviously is zero on the field theory partition function. And the way we did was we didn't originally we started from here and tried to find what the deformation operator should be to get from here to here.
Right.
But in the end, the prescription we have is more generic. What we do is the following. We say, okay, we want to solve this constraint. So we want a partition function that satisfies the Hamiltonian constraint. And on top of that, we want that this partition function satisfies the closure of these constraints in this particular way. So it's zero up to diff terms.
Yes.
So imposing these two things, turns out if you impose these two things, it tells you what O of lambda has to be.
Exactly, yeah.
Like the deformation operator.
Indeed.
So in a sense, I'm talking here about pure GR. The Hamiltonian constraint I wrote was for pure GR, but I can include matter terms or higher order corrections. I have a different Hamiltonian constraint. As long as I have satisfied the closure of general relativity, we can follow the prescription in our paper and tell us, this will tell us what O of lambda has to be.
Right, right. I mean, up to some details. When you have matter, for instance, it won't tell you what the potential of the matter fields has to be, just that there is a potential that separates the kinetic term and so on. Yeah.
In a sense that is specified here.
Yeah,
exactly. And this is very related to this equation, in a sense. If the deformation operator was not a long energy flow, it is equivalent to say that if you were to flow like this, you wouldn't take the constraint algebra from here to here. There will be plus other terms. There will be non-local terms. Right, so it's like you have to fine-tune the O of lambda such that this constraint pops out, and that turns out to be the same constraint as making sure that it satisfies the Kalan-Zemansky equation.
Right, right.
Which is an interesting connection.
Right, and I mean, the subtlety is that if you went here, there are certainly other ways to satisfy this if I integrated it over space. If I just wanted the commutator to vanish, or when I integrate and then have a truly sort of not local but global Hamiltonian constraint that needs to be satisfied, I could get away with a lot. When you need it to be local, right, and you need to get this D here, right? Meaning when you turn the scale into a function of space, right? When you can talk about local rescalings and the response of the quantum field theory under that, that's when it becomes very constraining.
But that is exactly what you have to do in quantum gravity.
Exactly, and that's what I thought was just like very deep back in the day. It's just now already several years.
So maybe we can go to the paper and see.
Sure.
Like to one or two examples of what O of lambda looks like.
Yeah, no, that would be very helpful.
I can also say one more thing.
You can say.
So, to give a bit more intuition about how to construct these operators, it's actually, although initially it was very, we did it in a convoluted way.
Very
painful way, because we had to do these commutators over here.
Yes.
But it is equivalent to the flow equation in the radial thing that people have been working on, and Tom Hartman and Samal Chico and a
And
lot of
him.
people and
Yeah.
Vasudev Shyam. So, but in the end of the day, everything boiled down to a very small understanding.
Okay.
And I'll just say that final refined understanding of what that construction is.
Okay.
So the goal is you start with a set of constraints that closes. Like for example, the Hamiltonian constraint and the diffeomorphism constraints, and they close. So the commutators of any two of them, they don't generate more and more constraints into your
Right.
theory. And so, given that, then you want is this equation? Yeah. You want to find something which satisfies the Hamiltonian constraint.
Yes.
And you also want to interpret this guy as an RG flow, and this to be some local counter terms.
Okay.
Now, one may ask, why not just take the CFT partition function? Why does it not satisfy the Wheeler-DeWitt equation?
Okay.
Because it satisfies the trace anomaly equation,
Right.
which is nothing but the W minus IA acting on Z CFT equals to 0. This is nowhere anything that looks like a Hamiltonian constraint.
Yes.
So CFT partition function, you cannot take it to be a Wheeler-DeWitt state. All right. But then why are we starting with a CFT partition function? That's because you start, if suppose you had a solution to the Wheeler-DeWitt equation, and you look at how it behaves in the limit of determinant of the metric tends to infinity.
Okay.
That is like, for example, you have a Wheeler-DeWitt state on a slice. It could be either a Cauchy slice or a radial slice. You take the determinant and blow it up to infinity.
Right.
Then in that limit, this equation effectively boils down to some equation which implies that psi of g in this limit,
Mm-hmm.
the infinity limit, is basically like e to the power of some local counter term times something that looks like a CFT.
Okay. Right.
This is
Yes.
what Laurent Friedel showed in his
2008 paper.
yes,
Yeah.
exactly. So now, good. Now, what is this thing? Essentially, you're doing a rescaling.
Yeah.
And under this rescaling, the Wheeler-DeWitt state becomes some sort of a CFT up to some local counter term. And so away from the determinant G tending to infinity limit, you can start, it would look like this, as this ansatz that you wrote down,
Mm-hmm.
in which this guy goes to
Right.
that CFT
Right.
in this limit, and counter terms something happens to it.
Yes.
Fine. So you want this to be an RG flow, which means this must satisfy this equation. When you hit W minus O on here, it must annihilate this whole thing. And so now if you look at W, it's a marginal term.
Mm-hmm.
And O, it has to have irrelevant terms.
Mm-hmm.
Only then under RG, it would go to this CFT.
Yeah.
All right. So now look at the Hamiltonian constraint, H.
Mm-hmm.
Now you start with a general Hamiltonian constraint. What
Okay.
would it have? It would have some terms which is relevant and marginal, irrelevant. All right. So look at general Hamiltonian constraint. It would have terms like which is relevant, marginal, irrelevant. Right.
Mm-hmm.
So now certainly, since the goal of the program was, if you start with H on this side and you commute it past this guy, it becomes the trace anomaly equation.
Mm-hmm.
And if you commute it past this, it becomes this something which has no relevant terms.
Yes.
the only way in which you can start with a relevant some term which has relevant terms in it, and when you commute past with it, you do not have relevant terms, is by killing off all those relevant terms with discounter terms.
Right, yeah.
So you specifically choose those counter terms which does the job of killing off all the relevant terms. This guy.
Yeah.
And then what you're left with is this, which would be of the form of marginal and irrelevant terms. And whatever irrelevant terms you have, just take them and throw them on this. And if you do that, we showed that this guy, when again commute past this, it would become the trace anomaly equation and it vanishes.
Right.
Essentially, so basically, in the end of the day, if you want any solution to the Wheeler-DeWitt equation, whether it matters, it doesn't matter what symmetry. It could be a gauge theory, or you could have strings or anything, strings in some background.
Yeah.
You just take that particular Hamiltonian constraint, look at what relevant terms you have, kill those relevant terms by choosing the counter terms.
Yeah.
And then
find whatever.
done.
Yeah.
You the leftover irrelevant terms, you filter them out and put it in O of lambda. You're just done.
Right. And this is interesting because it kind of reflects the fact that there's just this is a point made by Lukowitz, Sarosi, and Belin in their paper about the t-squared deformation and the gravitational path integral, that in some sense the flow equation for this object is like a diffusion equation, but it's a diffusion equation with potential that doesn't have regular boundary conditions. In order to get regularity in the boundary conditions of that equation, you need to specify this counter term.
Right.
Once you do, you can parameterize its solutions in the same way as you would with the regular diffusion equation. And yeah, the diffusive part is this irrelevant part that you're referring to. And the part that tells you it's like a diffusion equation, as in the term on the left-hand side, is this W.
Okay.
So it's a very nice story.
Seems like an interesting paper.
Huh?
Seems like an interesting paper.
So it's a very nice paper. Well, yeah. So they've done some very interesting things. They didn't want to push in this direction of going towards Cauchy slices. That's really like the thing that distinguishes your paper from the others. But I mean,
it's a very simple step. Like you have it to be a radial thing. Fine, it could be a radial cutoff, finite cutoff holography. But if just one step of interpreting it as also living on Cauchy slices, gives you states in a theory of quantum gravity.
Well, let's actually get to that. So in your paper, you've actually gone, if you don't mind, let me stop sharing. You've actually gone and explained how all of this works quite nicely. So first, let's jump to, okay, well, let's go in a different order, right? So let's first go, before showing you what O is, right? Strictly, let's talk about more of the relation with the Cauchy, or with the radial picture that we've talked about to some extent. And there's a way in which you can see the Cauchy slice, so the novel perspective, the truly very novel thing in your paper, with zero overlap with anything else, is this picture, in my opinion, which is you start with a Lorentzian system. Oh, sorry, you start with the Euclidean system, right? So the bulk is Euclidean, the boundary is Euclidean. And then you do the t-squared deformation as has been prescribed that you should do in order to pull the boundary inwards, away from the asymptotic boundary. And here you're in a setup where if you kept doing this deformation, you would eventually hit some place, right, in parameter space, where you can no longer interpret the generating function of this Euclidean field theory as being real. So what we in the literature have done is just stop there, right? You stop there and say that that's a finite patch of the Euclidean section of the spacetime you care about that we now have a holographic description for at some finite radius, right? But what you say is, what if you just proceeded? Well, to proceed comes at the cost of I appearing in various places, right? But the specific manner in which these eyes appear in this story is exactly in the manner to push you onto a Lorentzian Cauchy slice, meaning you can interpret now what was once the energy associated with some time-like boundary as just the object that would live on the Cauchy slice, so that when you take the derivative times I with respect to the metric, you produce the momentum conjugate or the expectation value of the stress tensor with a Lorentzian prescription with an I in the exponent. So that overall everything stays real, right? And here with the 2 and the 2 star is another very interesting and novel effect, which hitherto had not been noticed or commented on, which is a spontaneous breaking of time reversal invariance. Which, I mean, we can go into now, but we can also table that for just a bit. Basically, this is just to say that the O operator that you've written down here is not so different from the thing that would generate the radial evolution in the Euclidean case, right? In fact, it's quite the same. It's just that there are signs that change in the Hamiltonian constraint if you decided to keep pushing past this point. And those signs are actually the diagnostic of the signature of the bulk space into which the space-like surface has been embedded.
Yeah.
And this was also something that Laurent Friedel commented on in his 2008 paper. Yeah, but first let's jump to what O is. So where is the section where you write it down?
There's an example.
Yes, so well,
here.
Great. So the simplest O in D equals 2 is the TT bar operator.
So what we wanted to show in this line is exactly that by following our prescription, we recover the usual TT bar operator that people are used to from radial
Yes,
holography.
It's really the same thing.
Yeah.
One way you write a differential equation for the action.
Yeah.
In your partition function. Other thing, you just do commutators or modifying operators on the partition function. It's equivalent.
Right. So this is the simplest case. And more generally, and this is like, well, you had this one expression where you had everything that you could possibly worry about.
So that's the example there.
Yes. So scalar field is already quite a bit. But let's just see the shape of O. Do you have O here? Yes, here we are.
It's called X.
X, O became X, but that's fine. So basically you have what would be called the T squared deformation, which is 81 to 83.
Yeah.
And then you would have the so-called O squared or OO deformation, which is 84 all the way to 87. And
yeah, that's the matter part.
Yes. And if you went further, you would discover that in the intervening steps where you use the closure to show that this has to be the form of the constraint, that if you added a beta function here, right, like a general function beta phi, that it has to satisfy a gradient flow. And what's more, you can show that this potential V of phi has to satisfy so-called superpotential relations. So those are also, I mean, they're well-known results from holographic renormalization, which tell you that when you do holographic renormalization, the potential, so when you have scalar fields, their potential and velocities and everything satisfy the same kinds of relations that supersymmetric, like supergravity theories manifest, even though there's no supersymmetry here.
So are you saying that when we want to couple matter to gravity, in quantum gravity, there's a constraint on the potential for matter?
On what? Yeah, there's some functional relations that the potential satisfies. For reasons I still don't think we fully understand. They're so-called superpotential relations. So it basically
Where are they coming from?
They're coming from the fact that SCT is this counter term here can have arbitrary purely matter dependent terms, and then demanding closure of the constraints will relate the potential here to gradients of that counter term with respect to the matter field and to the metric. So you'll discover that the constraint equations, as they emerge here, take this form. But in addition, V is given by like gradient squared of something else. That something else is the counter term that would appear here. You call that a superpotential.
Here, it wasn't the potential like arbitrary potential.
Well, the thing is that the potential is arbitrary, but so is that other thing appearing in the counter term.
Yeah, for given a potential, you need to put counter terms, yeah, depending on what potential you have.
And that the dependency is the superpotential relation.
Yes.
Depending on what terms
So you'll
the
get
potential
some.
is. So maybe
That's
that'll
fine.
be.
So the counter terms and the O of lambda is fixed by all of that. But
we picked in
how
here.
does
We picked
that give a restriction on what Hamiltonian constraint you can start
here
with?
we picked a potential that didn't have more relevant terms, so we didn't have to deal with it.
So you just chose 5, 4, and you chose.
Maybe there is something that is generated. I don't know.
If it is not, if it had relevant terms, then we would have killed it off in the C.
Maybe
Exactly, but that's the point. So the
other
thing
stuff.
is that you'd have put something. You could put something quite general here, and you could put something quite general here. What would happen is that the quite general thing there would be related to the thing here, which would be related to the thing here. And those are the superpotential relations.
So wait, you're saying like if one starts with the Hamiltonian constraint, which violates the superpotential relation, you do this deformation, you will not get something to close.
Yeah, I'm not exactly sure because what you would discover is that the closure imposes that superpotential relation. Yeah. And the superpotential is a term appearing here, a very general term. So no matter what, so the rigid nature of holographic IG flows is that no matter what beta function appears here, right, it'll come from the gradient of that superpotential as you go to the asymptotic boundary, and that superpotential will be intimately tied to V.
Okay.
And this is how you derive various relations. You've already derived one of them probably, which is the relation between the masses and these conformal weights, but that's the first in a tower of relations you can derive. So yeah, we can break that down. It might be instructive to do that at some point. But anyway, for the purpose of what we're doing here, this is the general form gravity matter system can take. And so it's the same kinds of operators that we encounter in the radio cutoff story, except now what we have, it's harder to see, but trust me when I say that what we have are differences in I's and signs, and that these signs tell you that you're actually embedding this as a Cauchy surface, the space-like surface as a Cauchy surface within some Lorentzian space. And yes, that's kind of very interesting. But let's just jump back to this issue of T symmetry breaking, because this is another very novel effect that's been observed here. So
you can think of this. Okay, we have this nice picture of embeddings of the slice on some space-time, but the prescription we wrote so far that we discussed in this podcast was just there was a field theory partition function that lived on a slice sigma.
Yes.
Nothing was mentioned about anything else.
Yes.
Depending on a metric. And there was some deformation parameter parameterized by mu.
Yeah.
So what this picture is saying is, imagine you start at this point 0, in which you have the CFT partition function with a metric given by the boundary of Euclidean ADS. That's the metric you put on that slice. That is dual to, in a usual holography, that's dual to the gravitational path integral with Dirichlet boundary conditions given by Euclidean ADS. So it's just given, and it has a particular saddle point that is given by this Euclidean ADS geometry that goes all the way to this boundary at 0. Then let's say we turn on the deformation all the way to 0.1. Some finite but small amount of deformation. Still, it's just a field theory on a slice.
Yes.
Correct? And both at 1 and at 0, I could have computed the stress tensor expectation value, and it have been a real value. And now, what is this dual to at 0.1? Is dual to gravitational path integral up to this Dirichlet boundary condition, of which saddle point would be given by the filling of this Euclidean ADS geometry up to this one.
Yep.
Now I say you keep going. there will be a transition point in the field theory before we do all of this interpretation of saddle points in the bulk gravitational path integral, just in the field theory, the stress tensor keeps being real, the expression value keeps being real. But after this point, still real, but it's a sum of two terms which are complex conjugates of each other.
Right.
So there are two contributions, purely from field theory. Now, what does this look? What's the interpretation of this from the bulk perspective? The interpretation is exactly that you've entered the Lorentzian regime.
Yes.
In which case, remember that the only thing we specified on the slice was the metric. We didn't specify anything about the extrinsic curvature.
Right.
So, if you think about saddle points that are dual in this bulk gravitational path integral perspective, all we have specified is some Dirichlet boundary conditions on a slice. But if you think about the saddle points, that same slice with the same G could have been embedded here, like as in 2 or 2 star. And because the field theory doesn't pick which one it is, you actually have, from the bulk perspective, a contribution of two saddles.
Yes.
One which is the one with the going upwards in the Lorentzian regime, plus the other one that is going downwards in the Lorentzian regime. So the same one state on the slice sigma, given by this one field theory partition function,
Right.
encodes both future and past
Right.
in the Lorentzian regime. From the perspective of field theory, this is seen, as I said, by the fact that you have this transition point when the stress tensor expression value becomes a sum of two terms.
Right. Two complex terms.
Complex conjugate terms. So in a sense, this is what it's kind of like. You can see it as a spontaneous breaking of
the
T symmetry,
time symmetry, which is something we should comment a little bit on, because on the one hand, the Wheeler-DeWitt equation tells you that there is no such thing as time. On the other hand, we're saying that there's this T reversal breaking. And what made me understand this is to notice that when we compute the extrinsic curvature, when we compute the momentum conjugate to the metric, if you thought in terms of moving frames, as in if you thought in terms of the frame bundle, the split of space-time into space and time requires the specification of a normal, right? So you need to take your, say, tetrad in 4 dimensions and break it up into a triad and a normal, right? And so this frame specification is a sign's worth of information, essentially, right? So there's like an orientation to your space-like tetrad. Here, what's happening is that the breaking is in that orientation. Here you have a future-directed normal. Here you have a past-directed normal. And so it isn't that there's some global time that we're trying to track, although on the asymptotic boundary it is true. But like here,
all these slices are anchored at the same point.
Right. But I mean, we're not. You don't necessarily need the asymptotic boundary to make sense of the statement, right? So you could of course talk about T reversal with respect to just the corner pieces of the Hamiltonian constraint, right? As in, you could just use the asymptotic boundaries through time to talk about time reversals, but you don't have to. You could just use the one normal.
It's not like we don't have to. We cannot, because we are talking about this for one state, and that one state lives on one boundary Cauchy slice. So you have to fix the boundary point.
Yeah, you fix the boundary point, sure, but in the bulk, right? I mean, the point of time reversals being confusing is from the bulk perspective, because it's the bulk time reversals we're kind of talking about here, right? So in the bulk, if you went to the asymptotic boundary, right, you have a clock there, right? You have a time there, and you can talk about reversals with respect to that time. But I'm saying you don't have to make sense of this T breaking, right? So even if you did this in a compact universe, you would still have the one bit of information, which is the orientation of the normal, with respect to which you're computing the extrinsic curvature, to tell you if it's future or past pointing, right? So this is the one corresponding to having future pointing normal, and this is the one corresponding to having past pointing normal. And just the specification of the data on the Cauchy surface does not tell you which way to go.
And the prescription just gives you the sum of both contributions.
Right. And of course, I mean, the reason why you're saying there's a spontaneous breaking here is because, well, if you were tracking classical evolution, you can't really track what happens to a superposition per se, right? You look at one trajectory through the flow, it goes like this or it goes like this, right? If we were doing the full quantum Wheeler-DeWitt equation in whatever sense, in whatever corners we have access to it, then you're in a better shape, right? You can really say that there are these conjugate contributions, but it's a linear equation. I can superpose them, right? And I'm okay. So this is a very interesting point, and we're still sort of peeling away at the layers of this onion to get at.
From the Wheeler-DeWitt's perspective, this is a very simple point, and I'll tell you that.
Sure. Okay. Do you want to maybe share the screen again?
First, like some sort of understanding of the setup is required. Let me say that. So it's in everything other than quantum gravity, you have a background and you have some stuff in that background and you can quantize those things.
Okay.
Good. But in quantum gravity, the background itself is quantum mechanical.
Yes.
And so you don't have a background to start with. All you have is a state, let's say, which is, where is that thing? Psi of G. All right. Normal quantum mechanics, you have a state to live on a Cauchy time slice.
Yeah.
In quantum theory, you have a state to be living on a Cauchy slice. In quantum gravity, when you do not have a background, where does your state live? The only meaningful way to say where your state lives is on the boundary Cauchy slice. For example,
Boundary of the Cauchy slice.
You have the space-time and its asymptotic boundary.
Yeah.
So the notion of time is well defined only in the asymptotic boundary.
Yes.
Because a notion of background is also well defined only in the asymptotic region. The entire bulk, you do not a priori have a background.
Yes.
Because the background itself is quantum mechanical. And now consider a Cauchy slice on the boundary and call it dou sigma.
Mm-hmm.
So we are in a d+1 dimensional theory of quantum gravity. The boundary is d-dimensional.
Yes.
And this Cauchy slice dou sigma is a d-1 dimensional slice. So codimension 1 slice of the boundary. So you can only say that meaningfully Wheeler-DeWitt states live on this slice. All right. And what is G? G is just some metric on some hypothetical manifold sigma whose boundary is to be anchored at dou sigma.
Mm-hmm.
All right. So at first, when you do not have a boundary, sorry, a background, you do not think of sigma to be some Cauchy slices being embedded anywhere.
Yeah.
Only in certain cases where the geometry over here is classical, then you can start interpreting sigma with a metric G to be living on some Cauchy slices.
Right. Well, I mean, I guess it's an even more powerful point because you don't need I mean, it is true that, of course, having a geometry is a classical thing. But if you had this asymptotic boundary, right, and you just thought of the field theory living on that asymptotic boundary, and you had some mapping between its states and the other state, then the only surviving notion of geometry will be the asymptotic boundary.
Yes.
Mm-hmm.
Right? And what you do is you take the information starting from states of that theory, and you have a way of generating solutions of the Wheeler-DeWitt equation from it. Right.
Yeah.
So perhaps we should go to this. There's a reduction that you're referring to here, which is not just codimension 1, which is what people normally think of holography as, but effectively codimension 2.
That is
right?
Actually up to semantics. Whether
sure, yeah. I mean, if you're talking about states, but the important
states are always live in codimension.
Exactly, states always live in codimension 1 slices, but it's the same sense in which, like, normal physics that's deterministic has a well-posed initial value problem has a codimension 1 reduction already, right? Because if you just had complete access to information within some Cauchy surface, then you can just propagate it forward and you know everything that's going to happen.
Yes. That is not
right?
holography.
That is not holography.
Exactly.
That is just
so in
global
holography,
hyperbolicity.
Exactly. Holography, as in when gravity gets involved, there's a further reduction, right? So the effective reduction to codimension 1 has already happened, right? It's just what normal initial value problem of any well-posed hyperbolic system is giving you. But when you have holography, there's a codimension 2 reduction.
Yeah.
And this actually, well, I don't know how visible the blackboard is behind us, but we were having a discussion about the implications of this in this office. But we can first lay out exactly what we're talking about here.
So over
And-
here, if I plug in the metric G over here,
Yes.
now for example, in any geometry, you can always find some time symmetric slice.
Yeah.
And above that and below that, you can find the same metric G.
Yeah.
Now, so the G that you plug over here, how does the Wheeler-DeWitt state know whether it is the G of a slice that is above the time symmetric slice or G of the slice below the time symmetric slice? It does not. Actually, it encodes both of them.
Mhm.
And so in this, so when you start with the t-square, when you write the Wheeler-DeWitt state as a t-square deformed field theory, so initially, when you do a small deformation, the pi AB is that you get from it is imaginary. And so you, in the saddle point where you can think of it as being embedded in some Euclidean thing. And after you deform it sufficiently is when it splits into two branches, and one branch with positive pi AB and the other branch with a negative pi AB. So the Wheeler-DeWitt state splits into two branches, and one branch giving you information about the future of the time symmetric slice, and the other branch giving you information about the past of the time symmetric slice. And this is indeed needed to talk about Lorentzian spacetimes. So you have to deform the field theory past that k is equal to 0 slice. Yeah.
The same, this one state, you notice that here G is just an argument.
Yeah.
It doesn't define the state. You can put any G you want here.
Mm.
This whole one state has information about everything in the
Yes.
causal diamond
Yes.
that is anchored on this partial sigma
Yeah.
in the Lorentzian regime, but also has information in the Euclidean regime part that we had before up to the time symmetric slice that is encoded, also anchored on this partial sigma.
Yeah.
So it has information about all of that. That
Right.
the deformation tells you
How
everything,
to go. Yeah.
provided you specify the correct G.
Yeah. Yeah.
And the only thing that gets input into this is some information that lives on dou sigma.
Yes. Yes.
So what kind of thing that can live on dou sigma? A quantum field theory state.
Right. It's the, yeah, exactly.
So
Exactly.
essentially, it's like you just need to specify a quantum field theory state.
Yeah.
To give a Wheeler-DeWitt state.
Right.
And,
But this is exactly the engine of also, oh, sorry, I'm doing something. This is the localization to this codimension 2 thing, right? Of essentially all the information you in principle have on this codimension 1 thing, which when you have a well-posed initial value problem is all the information you need to go up or to go down, right? This is at the heart of like Surrat Arjul and collaborators approach to understanding the information loss problem, which is, I think, quite general. It's a very nice set of ideas because it's quite general, but it exploits the same fact, right? And I thought it was worth mentioning that parallel. Which, I mean, it's not even just a parallel; it's the same fact.
And in a sense, when we were in our attempt to solve the Wheeler-DeWitt equation, just popped out that all the information about the Wheeler-DeWitt equation was encoded in this codimension too. It's not like an input.
It's a consequence.
Yeah. Like
It's a
for
consequence.
example, let's go back to that map.
Yeah.
That map has everything. Okay, why are we calling this map? Now this is a field theory partition function, right?
Yeah.
This equation is really incomplete. Why? Because it's a field theory partition function on what? On sigma.
Yeah.
And what is sigma? It's a manifold with a boundary.
Right.
Sigma, dou sigma. So if you have a field theory partition function on sigma, and if it has a boundary, then the field theory is not defined unless you specify a boundary condition.
Yeah.
So let's specify the boundary condition.
Yeah.
Let's copy this guy. And all right. So a boundary condition needs to be specified, and let's call that as
Mm-hmm.
get correct. Now, how would you specify the boundary condition? in a most general way by some functional of that boundary conditions,
Mm-hmm.
and you integrate them. All right.
Yep.
So in the end of the day, what you get is this whole thing. Since it satisfies a Wheeler-DeWitt equation, you can now just call this as a Wheeler-DeWitt state, and which to specify a Wheeler-DeWitt state, you need to specify a boundary condition,
Yes.
which can be interpreted as field theory state
Yes.
living on dou sigma.
Yes. Yes.
So now what, in the end of the day, what do you have? You have a map from a field theory, which eats a field theory state and spits out a Wheeler-DeWitt state.
Correct.
So this is
That's the
the
full
boundary
dictionary.
to bulk Cauchy slice holographic dictionary.
Right, which means this is like mapping from like the Hilbert space of these, provided that that's a meaningful notion, to the Hilbert space of this, which gives it meaning, right?
Yeah. So
that's
already in holography, you have the holographic CFT. It already has a Hilbert space. So now this gives you a Wheeler-DeWitt state for any arbitrary CFT state. That is a point that needs to be stressed.
And also, like, notice that the deformation that you do is always the same.
yes,
The freedom is really only here.
yes,
In these boundary
exactly.
conditions. Like, so given a boundary condition here, you have a state here. Given a
Mhm.
different boundary condition here, you have a different state here.
Yep.
And the
Indeed.
state encodes given such a state, if it is a state that has a Semikaska interpretation, that it encodes all the information about it, the whole causal with patch.
Exactly. Well, that's very nice. So, in lieu of needing to be in another meeting, we should probably wrap up fairly soon.
Then I'll say one point. This map is a boundary to bulk map. It would be a useless map if it took two different QFT states and gave the same Wheeler-DeWitt states.
Mm-hmm.
And that does not happen.
Okay.
So it's really a one-to-one correspondence.
Okay. Well, could you explain why?
That is a whole argument to go into.
Okay, but you have an argument. Presumably, it's in the paper.
Yeah, it is there in the paper, a proof of
Okay.
why it cannot happen. And assuming something called generalized holographic principle, which you can take two viewpoints. Either you prove it, or you take it as a definition of the gravitational path integral.
Okay.
Second point seems more
Second
plausible.
point
More
seems
plausible.
more practical and interesting. And yeah,
Very
so the
cool.
gravitational path integral. Sorry, not the gravitational. The generalized holographic principle, in some convoluted way, implies that this map would be one-to-one.
1-to-1. Makes sense. I mean, it makes sense that you can use that as a condition for what you
Yes.
mean by defining the theory of quantum gravity.
Yeah. And this, when you evolve this state with the boundaries Hamiltonian, that is equivalent to evolving this state with the boundary Schrodinger equation, where the boundary time is now generated by the ADM Hamiltonian. So in that sense, the ADM Hamiltonian and the CFT Hamiltonian are the same.
Very nice. Very nice. Okay. Well, this is very fascinating. I thank you very much for doing this with me. And if you all have managed to stick around this long, please like, share, subscribe, and comment. There'll be a link to the paper in the description below. And yeah, these guys are applying, so please hire them. So Theoretically Podcasting, and we will catch you later. Hi all, this is Theoretically Podcasting. I'm Vasu Sham.
Sorry, I'll do it better next time.
Okay.
Why are you laughing, man? Look at myself.
Hi all, this is Vasu Sham, and we're Theoretically Podcasting. Today I have fucking dude. Hi all, this is Vasu Sham, and we're Theoretically Podcasting. Today I'm joined by Rifath Khan and Goncalo Regado, and we're going to talk about Cauchy slice holography, which is a research program largely spearheaded by these two and their supervisor, Aaron Wall.
Dude, you have to get this.
Don't say